Hello students, till now we have covered definition of sequence, right? Also we saw boundedness of sequence and convergence of a sequence, right? So a sequence AN is said to be convergent to L if a sequence AN is said to be convergent and it converges to L if limit of n tending to infinity AN is equal to L, right? Also this can be also written in epsilon delta definition, that is if for epsilon greater than 0 there exists a natural number m such that difference between a and L is less than epsilon for n greater than m, right? So this is what we meant by convergence of a sequence or convergent sequence. Also we did what is a divergent sequence. Divergent sequence is a sequence limit of which is equal to infinity, okay? And also we did oscillatory sequences. Oscillatory sequences are those sequences which are neither convergent nor are divergent, right? So now we are going to prove some results on convergent sequences, right? So first result is uniqueness of limit of a convergent sequence, right? It says if a sequence is convergent then it converges to a unique limit. Then it converges to a unique limit, okay? So pretty simple theorem. I'm just giving a brief idea about this theorem, right? About the proof of this theorem, right? So proof: if possible, what we are going to do in this, right? We are going to show that sequence if convergent, then it converges to a unique limit. That is, if AN is a sequence, it cannot converge to two limits, right? It cannot converge to two limits, or you will have to say that it always converges to a unique number, to a one number only, right? That is what we meant by uniqueness, okay? So we are going to prove this now. See how we are going to prove this. We are going to assume that if possible it converges to two limits, okay? We are going to suppose that, let us assume that this sequence AN converges to two limits. Then at the last we will be showing that this supposition is wrong, okay? Therefore it is not possible, hence a sequence converges to a unique limit, okay? So this we are going to show, right? So you will have to write if possible, suppose that the sequence AN converges to two different limits, okay? Two different limits, right? L and L dash. Okay, that is an converges to L also to L dash, right? So what we mean by this convergence, that is, therefore for epsilon greater than 0 there exist m1 and m2, because it is converging to two numbers, so therefore we will be having two natural numbers m1 and m2 such that an minus L is less than epsilon for all n greater than equal to m1, and an minus L is less than, okay, it is L dash, right, is less than epsilon for all n greater than equal to m2, right? So further you try to see what would be your difference between L and L dash. So L and L dash could be written equal to, okay, you just okay, 1 second before we do this. Okay, you can do one thing. Okay, we are going to see this definition is true for all the numbers which are greater than m1, and this definition or this inequality is true for all the numbers which are greater than m2, right? So if I take m equal to maximum of these two, m1 and m2, okay, then these both the inequalities are true for this m, right? So therefore an minus L is less than epsilon for all n greater than equal to m, and an minus L dash is less than epsilon for all n greater than equal to m. Okay, so I'm giving this equation number 1. Okay, so now further now let us try to look at the difference between L and L dash. So it would be equal to I'm going to do what, I'm going to subtract and add an in the middle of these two terms, and so that the net effect would be 0 here. So plus sorry, it is negative minus L dash, right? So it is equal to it could be written equal to an minus L, nothing, oh, one second. Okay, you just apply modulus inequality. Okay, we know a plus b is less than equal to, okay, so this is your a and this is your b. Okay, so therefore this is less than equal to L minus an plus an minus L dash. Okay, so we know minus sign is consumed by modulus, so we can write it as an minus L plus an minus L. Okay, further, since this is less than epsilon, okay, this is less than epsilon, this is also less than epsilon, so L minus L dash is less than equal to 2 twice of epsilon, right? So since epsilon is taken arbitrarily, okay, it could be as small as, okay, it could be very small. So therefore if epsilon is something very small but positive number, right, this implies it would have this difference must be smaller than that positive number. Okay, it could be epsilon could be 0.000000000, okay, up to so on this number. So what is the number which is smaller than this? This is 0. So okay, so epsilon, you can give a reason, right, like since epsilon can be very small, okay, so therefore this has to be equal to 0. So this implies L must be equal to L dash, right? So therefore supposition is wrong that these two numbers are not equal, right? So therefore we will have to say at the end that an converges to a unique limit if it converges at all, right? So this was the result 1. So now we are going to come to the second result. Okay, second theorem, result 2. Okay, prove that a convergent sequence is bounded. Okay, is bounded, right? And second is converse true, is its converse true, right? So proof. Okay, so what we want to show that if this is the relation, okay, this is the relation between boundedness and convergence. Okay, so relation implies if sequence is convergent, then it is always bounded, right? So this is the result, second result, okay, which we are going to prove in this lecture. Okay, so see, let an be a convergent sequence. Okay, now we shall show that, we shall prove that an is bounded, right? So how we are going to prove this? We will be we know when a sequence is convergent, it means an, limit of an is equal to some number L, that is for epsilon greater than 0, there exists a natural number m such that difference between a minus L is less than epsilon for all n greater than equal to m, right? Or then this can be also written, okay, we know if a is lesser than 2, it implies a is less than 2 and greater than minus 2. Okay, so similar is the case here. This is smaller than epsilon, we can write it as a minus L is less than epsilon and greater than minus epsilon, right? So adding throughout the inequality L, okay, we get an is less than epsilon plus L and L minus epsilon, right? So now further we can we just forgot to write one thing, for all n greater than equal to m and for all n greater than equal to m. I mean to say, what does this inequality mean? It means am1 plus am plus 1, am plus 2, am plus 3 up to so on, all these terms, okay, all these terms are greater than L minus epsilon and lesser than L plus epsilon, right? So this is the upper bound, this is the what we are going to show in this video. We are going to show that this is in this proof, we want to show that this is a bounded sequence. So therefore from here we get to know that these terms which are beyond am, these terms are bounded. Okay, so these are bounded by L minus epsilon and L plus epsilon. But what about some other terms like a1, a2 up to so on a minus 1? Okay, so we want to show this whole sequence is a bounded sequence. We do not want to only show that these terms are which lies beyond am, these are bounded. We doesn't want to show this only, we just want to show that this whole sequence is a bounded. Okay, so for this we will have to take maxima, okay, and minima. Okay, so take k is equal to maximum of L plus E or epsilon a1 a2 up to so on am minus n. अब देखो what is m here, this is maximum of all these numbers. ओके n नंबर में से सबसे बड़ा नंबर जो होगा, ओके ओके, for this that is the k, right? So for this k, all the sequence, all the terms of the sequence, that is a1 a2 a3 up to so on am1 plus 1, in sub terms these all terms are lesser than k now, because this is the greater number, greater of all these. ओके ये वाले सारे am के बाद वाली टर्म तो सारी एप्सिलॉन प्लस l से छोटी हैं, और एप्सिलॉन प्लस l हमने यहाँ पे इंक्लूड किया है, इनमें से सबसे बिगर नंबर लिया हुआ है. सो देयरफॉर वी कैन राइट an is less than k for all n greater than equal to 1. okay, or you can simply write for all n belonging to natural number. okay, तो इस तरह से we have proved that this is bounded above. Now we want to show that this is bounded below. For that we will have to take h is equal to minima of l minus e and a1 a2 up to so on a minus 1, right? And for this h, now an is less than greater than h, right? So therefore we have proved that an is less than k and greater than h. Thus we can say an is a bounded sequence, right? So now we want to show converse part, right? converse part का मतलब ये है कि उल्टा ट्रू है क्या, is converse true, that is if a sequence is bounded sequence, ठीक है, अगर सीक्वेंस बाउंडेड सीक्वेंस है तो वो कन्वर्जेंट होगी क्या, तो आंसर इज नो. बाउंडेड सीक्वेंस may not be convergent, right? Why cannot be it? Why? We are going to show this by an example. okay, so see, an is a sequence where an is equal to minus 1 raised to power n. We have already shown that this is a bounded sequence, which is a bounded sequence. Upper bound here is 1 and lower bound here is minus 1, right? These two are the bounds here, but this is not a convergent sequence. Why it is not a convergent sequence? Because the limit of n tending to infinity an does not exist. okay, so therefore this is not a convergent sequence, which is an example of a sequence which is convergent, which is bounded but not convergent. Therefore converse is not true, right? So now further let us try to look at the algebra of sequences. okay, algebra of convergent sequences. okay, so for this we are going to take two sequences, an and bn. okay, an is a convergent sequence which converges to a, and bn is again a convergent sequence which converges to b, right? Then firstly, if this is a convergent sequence and converges to a, then mod of an, this is also another sequence which converges to mod of A. Also mod of Bn converges to mod of B. Okay, secondly, if I multiply this k by an by k, okay, then this is another sequence which converges to k a, right? And if you add these two sequences, right, then it converges to a plus b. Okay, if you subtract them, then they again converge to subtraction of a and b. Okay, and an into bn converges to ab, and an by bn converges to a by b, provided b is not equal to 0 and an is not equal to 0. Okay, so I'm just leaving the proof of these for you, right? The pretty simple proof of these results. Okay, right? I hope you will do it by yourself. So I'm going to tell you some more results. Okay. Oh, okay. So again, okay, so for this we are going to again take two sequences an and bn which converges to a and b. So bn converges to b. Okay, so first result, if an converges to a, which I already told you here. Okay, if an converges to a and all the ans, okay, all the terms of this sequence are greater than or equal to 0. Okay, yes. Okay, if an converges to a and all the terms of this sequence are greater than 0, then a must be greater than or equal to 0. अगर सारी टर्म्स, किसी सीक्वेंस की सारी टर्म 0 या 0 से ग्रेटर है, तो उसकी लिमिट या जिसको वो कन्वर्ज करेगी वो नंबर भी, दैट नंबर शुड बी ऑल्सो ग्रेटर देन इक्वल टू 0. ओके, सेकेंडली, if an and an converges to a and all the terms of this sequence are lesser than 0, then a is less than 0, right? Third, if an converges to a and bn converges to b plus an is less than equal to bn. ठीक है, an की terms bn से छोटी है, their respective term, like you are comparing a1 with a1, a1 with b1, a2 with b2, and okay, it is lesser than this, a3 is lesser than b3, right? Then if this is happening, then their limit, or to what number they are converging, that is a and b, here a must be smaller than b, because all the terms of an are smaller than their respective term of bn. Okay, fourth, if an converges to a and bn converges to b, also an is greater than equal to bn, then a is greater than equal to b, right? So these were the few more results on sequences. Right, now we are going to do one more important theorem. Okay, sandwich theorem. Okay, sandwich theorem, or it is also known as squeeze principle. So see, what does this squeeze principle say? If bn is smaller than an and an is moreover an is smaller than cn. Okay, bn is smaller than an and an is smaller than equal to cn. Okay, for all natural number, for all n belonging to natural number, and okay, one condition must be this, and another condition is bn converges to L and cn converges to L. Okay, cn converges to L, bn converges to L, और ये वाली bn किससे छोटा है, an से छोटा है, और cn किससे छोटा है, किससे ग्रेटर है, an से. और साथ ही साथ देखो bn is lesser than equal to an and an is more further lesser than equal to cn, and plus this is converging to L, this is also converging to L. Okay, then an also converges to L. So this is known as sandwich theorem. Okay, let me give you proof of this result, right? Proof. So see here, bn is less than an and an is less than cn. Okay, plus one more information is bn converges to L and cn converges to L. Okay, so that is therefore for epsilon greater than 0 there exist m. Okay, m1 and m2, then you take maxima of these m1 and m2, and for that maxima of m1 and m2 you will be having both the inequalities true. So we can write it as in this way directly. I'm just giving the proof of this theorem. Okay, so therefore for epsilon greater than 0 bn minus L is less than epsilon and cn minus L is less than epsilon for all m. Okay, for all n greater than equal to m, right? So we know modulus inequality say bn minus L is less than epsilon greater than minus epsilon, and here cn minus L is less than epsilon greater than minus epsilon. Now you do what? Add this L throughout the inequality. Okay, epsilon plus e. So here also epsilon. Okay, here L minus L plus L cancel 0. So okay, so bn is greater than this. Okay, and cn is lesser than this. Okay, now we are going to take using these three, 1, 2, 3, combining these three parts we get, okay, 1 says bn is less than equal to an and an is less than equal to cn. 3 says cn is lesser than epsilon plus L, and 2 says, part 2 says bn is greater than L minus L. Okay, so this imply L minus E or epsilon is greater than an and an is lesser than L plus E. Okay, so now we can subtract throughout the inequality by L. So we get minus epsilon is less than an and minus L, and it would be E here, epsilon here. So therefore this implies an minus L is lesser than epsilon for all n greater than equal to m. Okay, so for all n greater than equal to m, this is true for all n greater than equal to m. So this imply, okay, so this imply limit of an when n tending to infinity is equal to L. So this is the proof of sandwich theorem, right? Okay, I hope you got it. Yeah, so therefore we can say an converges to L. So this proof was okay. What result we covered right now? What does sandwich theorem say? If an converges to, okay, if bn converges to L and cn converges to L, also bn के बीच में कोई और सीक्वेंस है, ठीक है, दैट इज an, तो ये भी किसको कन्वर्ज करेगी? L को कन्वर्ज करेगी इफ these two sequence are converging to L. So remember this thing, remember this map in your mind, that if an is less than equal to cn and it is greater than equal to bn, plus this converges to L and this converges to, this also converges to L, then this sequence must converge to L. Okay, so now we are going to take some examples, right, on this sandwich theorem. Okay, okay, find limit of n tending to infinity 1 over n plus 1 square plus 1 over n plus 2 whole square 1 plus n plus 3 whole square up to so on plus n plus n whole square. This question can be alternatively asked in this form. Prove that sequence an is convergent and converges to 0, okay, where an is equal to 1 over n plus 1 whole square, n plus 2 whole square up to so on n plus n whole square. Okay, so this is the an here. Okay, so solution now. So an is equal to this. Okay, we are going to prove this result by sandwich theorem. Okay, so one thing I just want to tell you here, see, this is a number, okay, 1 by 2, and this is another number 1 by 3. Okay, whatever number will be having greater denominator, that number will be always the smaller number. Okay, right? So similarly here, if you take this number 1 by n plus 1 and one side you take n, okay, so obviously one side you take n, okay, obviously this would be smaller number because denominator of this number is greater than this, so this number would be smaller, this would be greater. But if you replace here, we replace this number, this 1 by 0, but if you write instead of 1 n plus n, then this number will be greater than this. Okay, so same is true if you square them. Okay, if you square it. Okay, so therefore we can write (1 by n plus 1 whole square is greater than n plus n whole square or equal to, okay, in some cases, and it is less than equal to n only, okay, n whole square, okay. So keep this thing in your mind. Similarly, n plus n square would be greater than, okay, lesser than n plus 2 whole square and greater than n plus, okay, and lesser than 1 by n square, ठीक है, okay. So this would be true for all the terms, right, and so on. And last term is 1 by n plus n whole square. Obviously it is equal to, greater than equal to this, and less than equal to 1 by, equality holds here, okay, although we are writing greater than equal to, but equality holds here, right. So therefore this is the scenario, right. So therefore we can write, if you you can write 1 by n plus 1 square plus n plus 2 square up to so on plus n plus n whole square. This is less than equal to 1 by n square plus 1 by n square plus up to so on 1 by n square. यहाँ पे कितनी टर्म है, यहाँ पे कितनी टर्म है, n टर्म्स हैं यहाँ पे, तो यहाँ पे भी आपको n टर्म्स लेनी पड़ेगी. एंड दिस वुड बी ग्रेटर देन व्हाट, 1 बाय n प्लस n होल स्क्वायर. और कैन आई राइट इट एज 2n होल स्क्वायर? यस. और कैन आई राइट इट एज 4n स्क्वायर? यस, ऑफ कोर्स. up to so on plus 4n square. Again here will be n terms, right? So this is your a, okay, this is nothing but, so an is less than equal to n. So if I add all these terms we get, okay, ये n terms है, सारी same है, that would be n by n square, okay, and it is greater than equal to n by 4n square, okay. So n cancel here also, so an is less than 1 by n and greater than 1 by 4n, right? So this is your another sequence bn, and this is your another sequence cn, okay. You see bn का लिमिट क्या होगा, यहाँ पे 0 हो गया ऑब्वियसली, okay. So bn is equal to 1 by 4n converges to 0, and here cn equal to 1 by n converges to again 0, क्योंकि इसका लिमिट 0 होगा. जब आप n की जगह इन्फिनिटी डाल दोगे तो 1 by infinity is equal to 0. तो दोनों साइड, okay, if, okay, so see bn, if bn is equal to 1 by 4n and cn is equal to 1 by n, then bn converges to 0 and cn converges to 0, okay. Also you see bn is lying, an is lying between bn and cn, okay, and this limit is 0, this converges to 0, and cn also converges to 0, so therefore an must also converge to 0. So therefore limit of an tending to infinity is also equal to 0, or you can say an converges to 0. So this is how we use this sandwich theorem, right? So I think this is it for today. Rest of the things will be done tomorrow. Thank you.